Okay, welcome guys to session 6 of Hackschool, Intro to Leetcode. I'm Lorelai and this is Jeff. We're your Hackschool directors and we're going to be presenting for you guys today. Okay, so let's get into Leetcode. Again, here's a sign-in form. If you haven't attended a session before, which I think most of y'all have, it's the same form in the Discord every week. So if you just go ahead and fill out that sign-up form just so we can track attendance. And if you need help getting that, let us know. And then also in the Discord, we have the link to the slides, but if you need just QR code version, it's up here. And yeah. Okay, so this week is week 6 of our 7-week course of Hackschool. This year we're doing independent sessions, so this week is Leetcode. Today we're going to be going over what Leetcode is, how it's helpful. We're going to go over a mini side lesson about time complexity and Big O. We're going to go through common patterns that you'll find in Leetcode to help you get better at it. And then we'll go over some demo problems at the end. So let's get started with what is Leetcode. So if you guys are here, just a raise of hands, how many of you guys know what Leetcode is? Okay, does someone want to explain what Leetcode is? That's okay. Well, lucky for you, Leetcode is not just a meme. You've probably heard Leetcode everywhere when people are talking about CS Tech Bros. Everyone's like, oh, you got to Leetcode, you got to do 100 Leetcode problems a day. But it's not just a meme. Leetcode is actually a really helpful online platform that helps you with interview preparation. If you're interested in being in software engineering, software development, anything like that, Leetcode is a platform that helps you by giving you a lot of practice coding and algorithmic problems that's intended for users to practice their coding skills. Oftentimes, when you're applying for jobs and you get an interview back, you'll sometimes have a behavioral interview, which is more questions about yourself. And then you also have a technical interview, which employers and recruiters are going to test you on what you know and your skills. So Leetcode gained popularity among job seekers in the software industry and coding enthusiasts as a resource for those technical interviews and for coding competitions. So whenever you hear someone go, oh, I did a Leetcode easy, a Leetcode hard, those are practice problems that you can prepare so that you'll be more prepared when you go into your job interview. So oftentimes Leetcode can sound pretty scary. Everyone's really intense about it. They're like, you got to Leetcode every day. You got to do Leetcode hard. It's rah, 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 Leetcode. But we can talk about what it's not. Leetcode is not about memorization. The skills that you get from Leetcode aren't just, oh, let me do a bunch of problems and memorize how to do them. No, Leetcode is more about pattern recognition and problem breakdown. What we're going to be going over today to help you guys get better for this, to prepare you for your technical interviews, is about the patterns that you'll see throughout different Leetcode problems. So if you understand the basic patterns, you'll be able to apply them across different types of problems, easier problems, more hard problems, and then eventually in your future jobs. Leetcode is a website that tests for accuracy and optimization. So they want you to make sure that your code is working well using, again, the patterns that we're going to be discussing today, and also optimized, meaning that it's more efficient. Does that all make sense? Okay. Then to talk specifically about optimization, we're going to have to understand a really big term, which is Big O. Can anybody tell me what Big O is if you already are familiar with it? Yeah, go for it, Brian.
It's like how efficient like your code.
Yeah, basically, it's talking about efficiency. It's optimization. So Big O notation specifically is some sort of mathematical expression that describes time and space complexity. For our purposes today, we're just going to be talking about time complexity. Space complexity is also important when you get onto bigger projects, but for most cases, they're really only going to care about time complexity. And what that means is that it's going to describe runtime or memory usage of an algorithm as it grows with the input size. So say you're running a program and you have a list of n elements. You want to perform a certain process on that number of n elements. Big O is going to describe how long it's going to take to process those n elements as it gets from a smaller to a larger number. But yeah, as we're talking about time complexity, what we're not talking about is seconds. We're not talking about how fast something is in terms of like, oh, how many milliseconds is this going to take? How many minutes is it going to take? That's not what we're talking about. We're going to talk about how fast the algorithm scales. Because if you think about it, yes, for now, while we're in college, all of our problems are going to be pretty simple. You're going to be iterating through like a small-ish list, maximum like 20 elements maybe. But when you get into the real world and you're working on jobs, you're going to be processing millions and millions and millions of bits of data, a ton of information. And as that n gets larger and larger and larger, that's when those little changes in your code are going to make a difference in terms of how optimized your code is. So that's what big O is. You'll often see like graphs like these that tell you what like how big O scales. All you got to know, at least for this workshop, is that you don't want it to be like this. If it's like that, that means your code is going to get really bad. The more input elements you have, the longer it's going to take, and it's going to be frustrating if your code takes a lot of time. You want to get it as close to here as possible so that as you scale up, as your projects get bigger, it's not going to take as much time or as many resources. Does that all make sense? Okay, so yeah, again, we won't go into the weeds about how this works. There's tons of classes on complexity and optimization and stuff like that you'll probably take if you're in computer science. And if you've already taken CS32, have any of you guys taken CS32? Oh, no, not yet. Okay, well, you'll learn about this in CS32, so congrats. You have a little bit of a primer on what you're going to learn in CS32. But yeah, the big idea is Big O helps you understand all of these things. It helps you predict performance before running code. It helps you compare algorithms objectively, communicate clearly with other engineers. So like if you'll hear other people say like, oh yeah, my program runs at n of n log n time, you'll understand what that means. Be like, oh, that's like somewhat good. And then optimize for real world data growth and think like a problem solver, not just a coder. But yeah. So that's it for Big O. I'm going to hand it over to Jeff to go over the common problems that'll help you when you're solving your problems. And then at the end, we'll go through some demo problems.
Yeah, so let's go over some common patterns. These are like very basic types of algorithm strategies that you should know in order to solve these LeetCode problems. And they're very common in interviews. So as long as you like prepare one of these, or like there'll always usually be one of these types of patterns. And once you get good enough with these patterns, you'll be able to solve most LeetCodes. Yeah, a lot of LeetCode is just practicing these types of problems. So the first pattern we're going to go into is called two pointers. What that means basically is that what a pointer is basically it sounds complex, but it's pretty easy. It's just like you're referencing that element in that position of the array. So it's a common technique for arrays or stream problems. So as you can see in this example, we have two pointers. One is at the start and one is at the end. You can manipulate these pointers to do what you want. So for example, if you want the sum, if you want to find a sum, you can do like 1 plus 9 equals 10. And then you can move these pointers in like further into the array to achieve some kind of goal. And yeah, these two pointers basically just traverse the array and achieve what you want. As Lorelai said before about big O, there's a big O notation called O of n squared. So what that basically means is that if you've ever taken like CS31 and you know what like a double for loop is, that's kind of slow because it goes through every element twice in the array. So it goes through like, for example, you start at 1, it'll go through like 1 and 3, 1 and 4, 1 and 8, and 1 and 9, and it'll do like 3 and 4, 3 and 8. So that's like really slow, and that's called O of n squared because you're using two for loops. It helps reduce the time complexity to O of n, where basically that just means like you go over every element one time. So that reduces the big O like a lot, and it's pretty helpful. A lot of LeetCoding is just finding the most efficient solution. There's always like a clear, or there's not always, but there's usually a clear brute force way to do it, which means like doing the most explicit thing that you can think of, like using two for loops to find a sum. And two pointers basically just helps reduce that time complexity, so it's a lot faster. And we'll go over an example in the next slide. Here, let's say we have a target of 8. So we want two elements of this array to sum up to 8. And how do you do that? Like the most common or your basic instinct is just to take like 2 and 3 and 2 and 4, 2 and 5, 2 and 8, and then just keep going through the entire array until you find 8. But that's O of n squared. And there's a faster way to do it using two pointers is that, so you have to have a sorted array first. So if it's not sorted, you would need to sort it first in order to use this two pointer technique. Basically, you would just start at the start and have another pointer start at the end. And so what we can see here is that if you sum up 2 and 18, it's 20, right? So it's obviously greater than 8, which is the target. And the way you go on to the next step is that in order to reduce your current sum, you would move the right pointer to the left because all the elements to the left of the right pointer is less than the current right pointer. So basically we just move the right pointer 1 to the left, and now we have 2 plus 11, which is 13, which is still greater than the target. So you'll move left again. And now you have 2 and 8, which is 10, which is still greater. So you move left again. And now you have 2 plus 5, which is 7. And now that's less than the target. So now you want a number greater than 7, which you get that by moving the left pointer to the right, because every element to the right of the left pointer is larger than the left pointer. So now you have 3 and 5, and that equals to 5, which equals to 8, which is our answer. And as you can see from the past, like we only went through every element one time, and that's much faster than using 2 for loops to go through each element. So this is a very common technique, and yeah, if you study up on this, it'll be used in a lot of interviews if you guys are trying to find like some kind of sweet job that requires a technical portion. Yeah, so basically like the pointers will reference the indices, and from the indices you can get the element, and yeah, usually you just return the pointer itself. It gets a lot more complex for harder problems. Oh shoot, what's happened? Nudge it back. Sorry. Okay, great. Yeah, so here's another type of 2-pointer technique. This one is different from the other one, where both pointers actually start in the same place, and one is just faster than the other. It's called fast and slow pointers, and it's commonly used in linked lists. If you don't know what a linked list is, it's basically a type of data structure that holds data that points to another piece of data. So here you can see we have a starting node of 1, and that points to 3, which points to 2, which points to 5, and that points again to 3. And how would you find a cycle in this problem? There's no way to go backwards. So you have no way to figure out if you've actually been there or not, using like a common technique. So here, or using like what you explicitly think, because you cannot go backwards. So you can't meet together. So fast and slow pointers can help you find a cycle in this. So what this basically means is that both pointers will move in the same direction, but you have a slow pointer, which only moves 1 step at a time, and a fast pointer that moves 2 steps at a time. So if they both start at 1, the turtle will first go to 3, while the hare will go to 2. And then you keep repeating that until both of them coincide. And mathematically, this works out. I think there's like some kind of proof, but yeah, basically all you gotta know is that if there is a cycle, they will meet at the same time. So that's how you figure it out. Here's an example. You can see like both of them start here, and then the hare goes 2 steps, and then they eventually meet at the 5. And that's how you know there's a cycle in this in the linked list, which is pretty common. There's more advanced features where you have to figure out a cycle and do something else with that cycle. But here's like a basic application of fast and slow pointers. You guys have any questions? Okay. Another type of problem is called sliding window. And what this means is that you kind of have like a range of data in the array that you want, and you can move this window to the next part once you figure out if it is in your window currently or not. So if it's not, so let's say we start at 20, 10, and 30, and you want to like find a sum of 3 consecutive numbers. If 20 plus 10 plus 30 is not your sum, you would slide the window to the right one and then check again. This also helps reduce the time complexity from O of n squared to O of n. And yeah, it's pretty efficient, and it's also very commonly used. It helps avoid like recomputing work that you've already done. So if you use like 2 or 3 even for loops to do this, it'll be pretty inefficient. And yeah, so like sliding window is pretty helpful. Here is another example. So let's say we have an array of 1, 2, 5, 3, and 1, and you want to find the maximum sum of a subarray with size 2. A subarray is basically just like a 2 consecutive number, like a smaller array. So like here you would start like 1 and 2, and that equals 3. And then you slide the window over to 2 and 5. So it'll be like the first and second element. So you start at the 0 and the first element, and then you slide it over to the first and second element. You sum those up, that equals 7, and you slide it over again, that equals 8, and you slide it one more time until you can't sum it up or you can't slide it anymore. So it'll be 4. And then you can store all of these values in some kind of variable or like a max variable, and you'll see that your answer is 8, and this helps reduce your time complexity. Any questions on sliding window? And also like the sliding window doesn't have to be fixed. Some problems require you to like expand the window or shrink the window as well. Okay, so the next type of problem is called binary search. And it's basically a sorting algorithm that helps you find stuff faster. So if you imagine it like normally how you would sort like a stack of books is you would go through each element, or you go through each book until you find what your answer. But a binary search basically splits things in half. So you would take the middle element and compare it to the first half or the second half. Or you take your target value and compare it with the middle, okay? And then if your target value is less than the middle element, then you would search the left half. If it's larger than your middle element, you'll search the right half. And this is a lot more efficient than just doing like a linear scan over your array or whatever thing you're trying to search. And it reduces the time complexity to O of log n. And yeah, it's much faster than linear search. But like one caveat of this is that your array has to be sorted, or like it has to be sorted in a way where binary search, where all of the elements in the left half is smaller than all of the elements in the right half, or else it doesn't work. So here's another example. We have a sorted array from 2 to 91, and we can start off with the low, or we get the element of the low and the element of the high, and you want to find if 23 is in this array. So since it's given to us as sorted, then we can just perform binary search. Like if you're doing a linear search, you would have to go through like 2, 5, 8, 12, 16, and 23 to find your elements. And binary search basically expedites that pretty fast. First, you would find the middle element, which is basically just the low plus the high over 2 to find the middle. And you'll see it's 16, right? And that's less than our target value, which is 23. So then you would search the right half, which would be 16 to 91, or it would be 23 to 91 because you already checked 16. And then you would repeat the process. So now the middle is 56 and the low is 23. You check the middle, 56 is greater than 23. So we now look at the left half. So now you just have 23 and 38. And because the middle is the same as the key, you have found the target value. And that's basically how binary search works. So as you can see, it's like a lot faster than doing a linear search. All right, so now for some graphing algorithms. Do you guys know what a tree is? Yeah? Kind of? Okay. So you can see like the image on the on the right, it starts at like a root node. So all the bubbles are called nodes, and then the things connecting the bubbles are called edges. Basically they store some kind of data and are connected in some way. The two searching algorithms that these are DFS and BFS. It like basically finds an element within that tree. DFS is called depth first search and explores like a path fully until it reaches a dead end, and then it goes to another path and searches it fully. Breadth first search basically searches each level. So you can see on the graph there, the green one goes all the way down before it stops, and while BFS go through each level before stopping. Yeah, DFS basically you would go through each level and then you would backtrack up to go to another level, and then BFS just go through each level at a time. Some of these doing DFS and BFS is sometimes interchangeable, as it doesn't matter like what like it doesn't matter if like you'll always find an element if it exists in the tree. It just sometimes if you know that the element you're trying to find is closer to the root node, it'll be better to do BFS. And then sometimes if you know it's like really deep, it'll be better to do DFS because DFS searches every depth first, while BFS searches every level. And the runtime of this is O of B plus E, which means each vertex plus each edge. And the vertexes here are each node, and then each edge is each line connecting each node. This makes sense because in order to search through the tree, you have to go through each vertex and each edge. Okay, and yeah, so here's an example of BFS and DFS. For BFS, we go through each level first. So you can see B, C, and D are only one level away from A. So those we're searching first. So it'll be A, B, C, and D. And then the second level will be E and F. So we go to C. We see that E and F is one level away. And then this is the order that it scans these elements. So it'll be A, B, C, D, E, F. For DFS, it'll go through each level first. So it'll go through, it's like, it depends on your algorithm, how you implement it, but it's basically random which one it goes through first. Here it goes through A, D, F, and then reaches a dead end because F is a leaf node where it has no more like connecting dots it can go. So it goes back up to C, and then it goes down to E again, and then E is also a leaf node, so it stops, and then it goes to B, and then B is the last node that you need to traverse. So there are no more nodes here, and the algorithm stops. Yeah. Any questions on BFS or DFS? No? Okay. Another one is called greedy. And basically how this works is that it builds a solution from the most local option or the best local option, which means if you're starting at some point, you would just choose the best option from that point. And in the end, when you finish your algorithm, it'll be the overall best solution. This idea can be a little tricky to wrap your head around. And then there's something called dynamic programming later that builds off of this, or it's pretty similar. And yeah, basically greedy usually runs as an O of n log n, or when you have to sort something. So greedy, usually you can sort something and then choose the best option, or O of n when you don't need a sort. It's O of n because if you think about it, it only needs to traverse one time because you're picking the best local option. So you wouldn't need to go back to that option because you already know that's the best option. Here's an example of it. So let's say you want to find or I guess it's not the max value of coins, but it's the least number of coins that you need to sum up to 68. And basically, or I can change that right now, actually. Okay. So basically you would want to find the least number of coins that sum up to 68. And how you would do that is basically just pick the best option from your current starting point or whatever point you're at. So when you're at 0, so you have zero value, you would want to pick 25 because it gets you closest to 68. So then once you have 25 again, you can pick 25. So now you're at 50. And because you can't pick 25 again, you pick the next best option, which is 10. And then that gets you to 60. And then now you can't pick 10 again because then it'll go over 68. So you would pick 5. So you're at 65. And then finally you pick 3 ones. And yeah, that's basically what greedy is. You want to pick the best local option. And the last pattern that we're going to go over is called dynamic programming. It's basically used when a problem can be broken down into smaller overlapping subproblems. And instead of recalculating results, DP stores answers, usually in some kind of array that you can access later. Like it stores your pre-computed work, and then you would access them later to figure out what your best option is at that time. and it usually improves runtime from O of n squared to O of n. Sometimes it's more confusing than that, but that's like the general time complexity. Yeah, so here's an example of the Fibonacci sequence. So the Fibonacci, I'm assuming you guys know what the Fibonacci sequence is. It's basically like if you want to get the fifth sequence, you would add up the fourth and the third sequence. Here you can see that there's a lot of recomputed work. So like we compute 3 here and then we recompute it over there. So like why do that when you can save the third Fibonacci sequence for later? So here we compute the fifth Fibonacci sequence using 4 and 3, but in order to compute 4, you need 3 and 2, and in order to compute 3, you need 2 and 1, and from 2, you need 1 and 0. So from 1 and 0, you compute 2, and then you save 2 somewhere, and then compute 3, and you already know what 1 is because that's just 1, and then you store 3 somewhere, or you store it usually in some kind of array. So it'll be like a 1D array where each index will represent each element in the Fibonacci sequence. So since you computed 3 already, you don't need to compute it again when you need to sum up 4 and 3. So it's much faster. You save all of the red work, and then you only need to compute the blue work you see here. So yeah, it's a lot faster. You guys have any questions on any of the patterns that we went over? If not, we're gonna do some problems.
Are you already logged in?
Yeah. Hey, you wanted to do this, right?
Yeah. Yeah. let me do- Okay, do you guys already have a Leetcode account? Okay, if you don't, you can just make one, sign it with Google or something. Really does a huge, legal. Yeah, but today, just for now, have you guys done Leetcode problems before? Or have you not done any? Okay, awesome. If you guys haven't done any, because two-sum is literally like the ultimate beginner Leetcode problem. But yeah, so let me zoom in. Can you guys see that? Let me zoom in. Okay, now you can see it. Okay, so two-sum is like the introductory, like rite of passage Leetcode problem. The problem is given an array of integers num and an integer target, return the indices of the two numbers such that they add up to target. You may assume that each input would have exactly one solution and that you may not use the same element twice. You can return the answer in any order. So yeah, you're trying to find, so you're given an array. Actually, there's examples here. So examples, you're given an array called nums. It's just gonna have a bunch of numbers in it, in whatever order. They're not sorted or anything like that. And then you're also gonna be given an integer called target that you're gonna want to find if two of the numbers in this array can sum up to that target. That's why it's called two-sum. So yeah, so in this example, the output would be index 0 and 1. You guys are familiar with indexing, right? Like the first element of an array is 0, second is, okay. So 0 and 1 because 2 plus 7 is equal to 9. In this example, like this is your nums array, you got 3, 2, 4, and your target is 6. The output's going to be index 1 and index 2 because 2 plus 4 is equal to 6. And then this last example, if you have nums 3 and 3, target is 6. The output's going to be 0 and 1 because 3 plus 3 is equal to 6. So when we're trying to solve this problem, oh, there's also constraints. Yeah, these ones are, yeah, they're important sometimes if you need like specific edge cases and stuff like that. But for this one, because it's pretty easy, you can guarantee that 2 is always, or that the length of nums is always going to be greater than 2 and less than that huge ginormous number, so your runtime's not going to be crazy. And that the numbers are not going to be too large and that the target isn't going to be too large. But yeah, so now that we've seen this problem, let's work through it together. Does anybody have any intuitions as to how to approach this? You don't have to think about efficiency yet. We're going to go through a brute force solution, and then we'll go through the optimized solution. But yeah, brute force, what are your guys' intuitions? Anybody have any ideas about like loops maybe? Well, we can go through a sample one. So, oh, your Leetcode is weird. Okay. Oh well. So we have two-sum as the name of the function. Have you guys coded in Python before at all? Okay, so if you coded in Python, you're probably familiar with this syntax on the right, but yeah, we're just gonna declare a function to some. Usually in Leetcode, they'll give you the function declaration already. But yeah, let's say we want to brute force this solution in the most intuitive way. Let's say that if we're given, I'm gonna scroll back down to the inputs. Like say for this example, like this is our array. Like Jeff was saying before the 2-pointer methods, you can use nested for loops. So let's say you want to check like 2 and 7, 2 and 11, 2 and 15, 7, 11, 7, 15, 11, and 15. Just go through all the options, see if any of them is going to sum up to the target. And once you find the target, just return it. So the way you would do that in Python is for I in range nums. Oh wait, no, length of nums. Because we want to iterate through all of the elements in nums. And then we're going to do a nested loop to check all the ones after it. So what is going to be the range here? We're going to want to go from the one after it to the end. So it's going to be what? I plus 1 all the way to the end. I plus 1 to length of nums. And then you're going to do if, let's say, nums I plus nums j equal the target. Return I j. And then if it doesn't work, just return an empty list. Does this solution make sense? Yeah, so this is just how the layout of Leetcode is. And then when you want to test it, you can click submit. There's also other features, like you can time yourself, like with a stopwatch. Like sometimes you have like timed OAs or online assessments for jobs, and they're going to be like, oh, you have this amount of time to solve this problem. So you can practice by timing yourself, but it's just a demo for now. Oh, and here we go. So here's what we were talking about with runtime and complexity. So right here, we can see that our solution for now, this brute force solution, took 1,779 milliseconds, and it beats about 18.35% of the solutions that are on this website. We can see we're like right about here. And that's the other thing that's helpful about Leetcode. You can compare your solution to a bunch of other solutions that other people have come up with because there's so many ways to solve these problems. But yeah, so we're like right about here, and we want to get all the way up to here because we want our solution to be efficient. Like say for example, like nums is like 1,000,000 characters long. Yeah, this solution is going to take forever because you're going to have to do 1,000,000 squared computations. Does that make sense? Yeah, so this is sort of the layout of Leetcode and stuff like that. Okay, so let's try this again. Let's say, so now we've tried the brute force solution where we have 2 nested loops and we're just going through each of them. What are some things that we could do to make the solution faster? Say like we only want to go through the list once, or maybe we can store some values about elements we've already visited. Anybody got any ideas? Just throw them out there. Could use 2 pointers? Yeah, we could do what Jeff did earlier with 2 pointers. There's actually an even faster way than that, but that's a good intermediate approach, and that'll probably get you somewhere like in like a 75% range. Maybe a higher space complexity, but like not by much. But yeah, that's a good idea. Yeah, 2 pointers is a good idea. Actually, that's kind of funny because 2-sum doesn't use any of the patterns that we went over because it is a simple problem. But we promise that like most of the Leetcode problems will use the patterns that we went
Yeah,
over.
a lot of the easy problems don't use like algorithmic
Yeah,
like things that we just
like 2 pointers or
they're usually medium problems, but like these are like more intuition.
yeah. The point of this sim is just to get you familiar with the Leetcode interface and stuff like that. But just for the sake of time, I'll give you guys sort of the conceptual way of what we're going to be doing. So notice that right here, we're adding 2 different elements in the array to figure out if they lead to target. If we want to find a way that we can reduce this to O of n, aka you only run through the list at most 1 time, what we can do is we can use sort of a combination of dynamic programming, but not really, where we save what we've already seen by storing its complement. So I'm assuming you guys all know like addition and subtraction. So when you subtract a number, like when you, like say we're taking like 9 minus 2, its complement is going to be 7, right? Or the difference is going to be 7. AKA if any of the other elements in the list are 7, that means you have 2 elements in the list that are going to equal 9. So let's see how this solution is going to work. I'm going to have the syntax on the side so I don't mess it up. We run into bugs. But yeah, and also the solutions that we're going over right now are also on the slides, and they're also everywhere on the internet. So if you're ever confused about that, oh, you guys haven't taken 32. Do you guys know what hash maps are? Okay, so a hash map is basically a form of, it's a type of data structure where you can store information. Do you guys know what an array is? Yeah. So an array stores information, lists store information, dictionaries, maps, all of these are different types of data structures that can store information. A hash map is a type of data structure where you have a key and it will automatically take you to whatever that key maps to in O of 1 time. Like it only takes 1 access. It's super, super fast. More of the story, a hash map is a super, super fast data structure. In Python, the syntax is really easy. It's literally just brackets. You can just store information like that. And then, yeah, so we're going to do one loop. So for I in range length of nums, we're going to store an element called complement. So complement is going to be the target minus the current, what's it called? The current element. So what we have now is we have an empty hash map that's going to take at most 1 access. It's going to be super fast to access whatever element is in that array. And then we're going to loop through each element of the array. And as we go through, we're going to take a complement of that number, aka like 9 minus 2. That's going to be 7. So we're going to check if the complement is in the hash map. And if it is, that means that 2 of the numbers in the array add up to the target. So we're going to return the current index, which is our current number, and the index of that complement. Oops, wait. Sorry, Python uses brackets. Yep. And then, yeah, so that means that if we already have its complement in the hash map, that means that we've already found an element that you can add to the current element that's going to equal the target. And then if it's not, then you add that complement into, or you add the current element into the hash map. And then if you can't find it, return. Does this solution make sense? It's a pretty cool solution because with this, you only have to go through each of the elements at most 1 time. And so we're going to submit this solution. It's going to run. Oh, did I do hash map? Oh, nums. Haha, debugging. So fun. Perfect. So yeah, so see, that ran pretty much like instantaneously. Like we have 0 milliseconds, it beats 100% of the other test cases. We're all the way at the top here. This is what you want for when you're solving Leetcode problems. And if you can come up with a solution like this in a technical interview, your recruiter's going to be very impressed. But yeah, that's pretty much the basics of Leetcode. And I think we have time for a couple more demo problems if, yeah.
For this one, I'll do one that we actually learned. So, let me do this. Yeah. So basically, if you guys don't know what a palindrome is, it's basically just a word, or in this case, it'll be a sentence that is the same forwards as it is backwards. So you can see like here, it's if you reverse this string here, it'll be exactly the same if you read it backwards. In this problem, it's more confusing because it converts all uppercase letters into lowercase letters and disregards all non-alphanumeric characters. So what that basically means, it disregards all special characters like exclamation marks, periods, and stuff like spaces. It only allows, like it changes this string here. So like this would be a sentence. It replaces all the spaces and like the commas. It disregards the uppercase. It makes it lowercase. And yeah, it just concatenates all the digits or letters into one string without spaces or any special characters. And yeah, do you guys have any like so this will apply one of the themes that we learned today. Do you guys like have an idea of what type of pattern this is. So you guys think about it like just if you have a word like what's a palindrome? You think of a
Race
palindrome?
car.
Race car? Oh, like a one word palindrome.
Race car's one.
Oh,
Maybe.
is race
Is
car
it?
one word?
Maybe. I don't know.
I think it's two words. It's two words.
That's one of
Well,
mom, dad.
Okay, yeah. If you have mom, how would you determine whether that's a palindrome? Like, would you use loops? What would you do? Give you like a minute to think about it, and then I'll go over like what kind of pattern this is. For now, you can like ignore the uppercase, like the stuff about the uppercase. Just imagine it's all lowercase without any special characters. We can get into like determining whether there's a special character or not later. Um, yeah. A lot of questions also use palindromes as um like as a sub problem. So like a lot of medium problems will use this type of palindrome like intuition. Some of them like get a lot more difficult. But this is like a basic question, or it's like one of the fundamental questions that you should know for Leetcode. So just throw out like an idea, like what pattern? Anyone have an idea?
2 pointers.
Yeah. So we can use 2 pointers here. Basically, how this strategy works is that you want to like remove all the special characters and then convert everything to lowercase. And then if you have a pointer here and a pointer here, what you can do is just keep iterating over every letter. And then if they meet in the middle, that means it's a palindrome because you just compare the letters. These should be the same. And then you go one in again. These should be the same. You go one in again. They're all the same. So if you meet in the middle and every like if it manages to meet in the middle without returning false, like if this was like a B and then this was still M, you would go one in, this would compare a B to an M, and that would not work. So you would just return false. So the problem would be false. And basically, yeah, let's just get into the implementation. So you would want one pointer to reference the start. So that would be the 0th element, which would be like the start right here. And then you would want a pointer at the very end. And the way you get this is by, let's say you have the right pointer, which is the one at the very end. And then that would be equal to the length of the string minus 1 because strings are 0 indexed. So basically, in order to get this one, this point here, you would do the length of the string minus 1. Yeah. And then you would use a loop to loop until the left is equal to the right or the left is greater than the right. That would mean that they met together without returning false. So we can use a while loop for that. So you would do like a while loop. If the left is still less than the right, then you would continue doing the loop, essentially. And if it stops, that means the left is equal to the right or the left is greater than the right. And then we can return true at the very end. So you return true. Okay. So then what would you do inside the loop? Basically, you would just want to compare the left to the right. But in this problem, it also allows like special characters. So you would first check if, so you would do a check if the left is actually a, is, I think there's a, actually, I'm not sure what the command is. I think it's al num. You can search this up and then, yeah, there is a method in Python called isAlNum. This basically determines whether it is an alphabet character or a number. So you want it to be an alphabet or a number. If it's not, then we can just, if it's not an alphabet or a number, you would increment left because we don't care about the special characters here. So you would increment that by 1. So let's say this started with an exclamation mark or a space. You would just move it over, and then you only want the alphabet or digits. You just ignore all the special characters. Yeah. So you would do this, and then you continue the loop. So basically this stops everything else and then goes on to a next iteration of the loop. So it checks the left again. And then you'll do the same thing as the right. So if the right is not an alphabet or a number, then you would subtract 1. Yeah. Because this one, you're going leftwards, so you would subtract by 1. And then you would also continue. And basically, you also want to check. So now that you know that the left and right, if it passes these 2 conditions, that means the left and the right are both alphabet or digit characters. Yeah. So then you would want to check whether they are not equal. If they're not equal, then you can immediately return false because that means the string is not a palindrome. And the way you would do this is because this like uppercase characters can also pass the is al num, then you would want to first convert it to lowercase characters. So you can do this by or actually I forgot to do this, but you would need to check because the left and the right are still indices. You would need to check the element first. So you would also do if s left, which just takes the element at the left index, you would convert it to lower. So there's a command in Python where basically it takes a a character and converts that to lowercase. So you basically just want to compare that to lowercase. And if it's not equal to the right one, if it's not equal, you can immediately return false because that means that there is a digit here and a digit here that are not the same, which means it's not a palindrome. Okay, and then now if they are the same, it would pass the if statement and it wouldn't return false. So that means you know that this character and this character both pass the palindrome check. And then you want to increment left by 1 and then decrement right by 1. So basically you can just do left plus 1 and then right minus 1. Okay, and then if it passes all of the conditions, then you know that if it passes this, that means it reached the middle, and that means all of these from here to here and here to here are the same. So that means it is a palindrome, and yeah, it should return true if it escapes the while loop. So we can try running it. So usually when you press this button, it'll run it on the examples that it gives you. If you want to create your own example, you could, I believe there's a button. Yeah, where's the button? Here, okay. And then you can just create your own example. So let's say I want to do race car. And this should also pass this test case because race car is a palindrome. So yeah, you can see here that returns true. So yeah, another thing that you can also look at is some of the constraints. Sometimes that's useful. If these numbers, since it's so big here, this is like more advanced, but like you can look at these numbers and if it's a bigger number, that means the complexity should usually be like smaller, like O of n or something. If this is only like 100, then you can just think of a brute force method and that'll usually be true because the larger your data is, the faster you want your algorithm. So if it's like a very small number here, you know that your time complexity should be pretty high. So then you don't have to think of a more efficient solution. You usually like, if you can think of a solution, that would probably be the right answer for those types of problems. Yeah, so if you wanted to make your own, you would go here and then create your own test cases. And then you could also, so like once you're done with this, if you pass the test cases, you would submit it. And then it'll tell you some stats. Yeah, so here you can see that our solution is pretty efficient as it beats 80% of like everyone who submitted a solution. Usually if you're in this range, that means your solution is pretty slow and you should think of a faster solution. If it's like around 50%, that means you probably thought of the fastest solution. And then, but like these complexity measures are not always accurate. And yeah, like you shouldn't always trust what it says over here, as long as like above like maybe like 20% or 10%, like your solution is fine. And yeah, you can see our space complexity is also pretty good. Um, yeah. Do you guys have any questions on this? No? Do you guys want me like to go over another problem, or we can just end it here today? Okay. Yeah.
Is this helpful though?